We've been talking about ways to describe a function. I think we're on the sixth one now. So we talked about domain and range, positive, negative, zero, increasing, decreasing constant, extrema, end behavior. And this is the last one we'll talk about. This will be the last topic in chapter 6 or chapter 1. This first chapter that we're just doing together. So this last way to describe a function would be as a transformation of a parent function. And now there's a lot of vocabulary in that statement that you're probably not sure about, and that's okay. We'll unpack what we mean in this statement here over the course of the lesson. So because you read this and you're like, I'm not sure what that means, that's okay. We'll kind of define what we mean and describe and do some examples, and it should be relatively clear by the time we're done what we mean. The first thing that I want to talk about is, what do we mean by this word transformation? If you remember last year in geometry, you guys talked about 4 types of transformations. You talked about translations. And what happened in a translation is you had like a shape and it slid or was shifted up or down or left or right. You guys kind of remember that from geometry, talking about that? So when we perform a translation, the size of the shape remained the same, the orientation of the shape remained the same. The only thing that changed was its location. Basically, you picked it up and moved it to a new spot. But you didn't spin it or flip it. All you did, or stretch it out or anything, you just picked it up and moved it. Everybody kind of remember that? Okay. The second kind was a reflection. So there are a couple of different kinds of reflections you could talk about. You can reflect across the x-axis or the y-axis. When we do a reflection, the size of your shape stayed the same. The orientation could potentially change, right? In the example that I drew there, the triangle is flipped upside down over the course of the reflection. And the location is certainly changed. But the size of the shape itself has remained the same. Everybody okay with that one? Again, hopefully you remember that from geometry, at least like what we mean by reflection. The next one is called a dilation. So in a dilation, you're going to like stretch the shape out to make it either larger or smaller. So if we perform a dilation, the size of the shape definitely changes. The location potentially changes. The orientation should remain the same. So notice this triangle is still pointed up. It hasn't been changed to point to the down or left or right or something. Everybody okay with that idea? There's one other type of transformation you guys talked about, and that was a rotation. We're not going to worry about rotations in this class. That's a topic beyond the scope of this course. But the first 3 we will. So if we think about it, the triangle that I've drawn there is just a set of ordered pairs, right? We have infinitely many ordered pairs that describe those three sides of the triangle. Everybody agree with that? A function is also just a set of ordered pairs. It stands to reason that if I can perform these transformations on a triangle, which is a set of ordered pairs, I could perform the same transformations on a function, which is also just a set of ordered pairs. So that's going to be the big idea here, is applying these transformations to a function. And the type of function that we're going to be thinking about is called a very special thing. It's called a parent function. So a parent function is just the simplest version of some type of function. So let's look at some examples of different types of functions and their respective parent function. So I think everybody said they remember talking about linear functions in their Algebra 1 class. The parent function for the linear functions is just y equals x. A lot of us remember talking about quadratic functions in our Algebra 1 class. The parent function for the quadratic functions is y equals x squared. Some of us remember talking about absolute value functions. The parent function for an absolute value function is y equals the absolute value of x. At this point, hopefully you get the idea of what we mean by a parent function. We'll define that for when we talk about each of these new types of functions that we'll talk about over the course of the year. But it's basically just the simplest version where all we're doing is taking whatever the operation is in question, and that's the only thing happening to the x. So we're just squaring the x, or just taking the absolute value of the x, or when we talk about radical functions, be taking just the square root of the x. So it's just like one thing happening. Everybody okay with that idea? Okay. So here is the big idea then. So we can say that every member of a type of function can be described as a transformation of the parent function. We'll recall f of x in this definition, the parent function. So we can write any function in that type as y equals a times f of x minus h plus k. And those a, h, and k are going to indicate to us what kind of transformation is going on. So what we're saying is that if I talk about the linear functions, all the linear functions kind of look like that parent function that have been altered a little bit some way. They've shifted left or right, or they've been stretched out or shrunk down, or been reflected across one axis or the other. But they're all basically still that parent function, just we've done some transformation to change the shape there a little bit. Just like if you think about members of a family, they all kind of look a little bit like their parents. They're obviously different and a different version of them, but there's still like some resemblance. That's the kind of the idea here. So how do we tell what type of transformation occurs from the a, h, and k? There's 4 kind of rules or criteria that'll tell us how to do that. So the first thing we'll do is we're going to look at the sign of A. And if that value for A is negative, then a reflection across the x-axis occurs. If the absolute value or the magnitude of A is not 1, then either the magnitude of A is greater than 1 or the magnitude of A is less than 1. If it's greater than 1, we have a vertical stretch. And if it's less than 1, we have a vertical shrink. I was running out of space, so I abbreviated vertical with V dot. The third thing we need to look at is the value of h. If h is non-zero, then something is going to happen. If the h was positive, it's going to shift the graph to the right that many units. And if the h is negative, it's going to shift the graph left that many units. Lauren? And the fourth thing is the k. So if the k is non-zero, something is going to happen. If that k is positive, it's going to shift it up k units. And if that k is negative, it's going to go down k units. And we'll do some examples here in a moment of kind of how we can use this information to make some predictions and do some graphing and describe kind of what we'd expect to see. Yes, sir. Of course. So, of all of the things we've done in Chapter 1, this one is going to be extremely important, not only for the rest of this course, but going forward into trigonometry and pre-calculus next year. because all of the graphing that we're going to do throughout all of these courses is going to be based on this idea. So this set of criterion you will definitely want to have committed to memory. Like, you don't need it memorized word for word, but you need to have it memorized well enough that you can do things with this information and you know this information. It doesn't have to be like word perfect memorized, but you have to know, like, when A is positive 5, what does it do? Or when H is negative 3, what does it do? And how to pick out the A, H, and K from looking at the function. So we'll do some examples to kind of help practice that. So let's say we're asked to describe the transformation of f of x. And we have y equals negative 3 times f of x plus 2. The first thing that I'm going to want to do is identify the values for my a, h, and k. The way that I'm going to do that is I'm going to look at the general form that was described in our definition above and use that to identify my values for A, H, and K. So looking at our example, what is the value for A? Negative 3. Everybody happy with that? What's our value for H? What was that? 0 is correct, right? If I have x minus 0, that's the same thing as x, which is what's in ours. Everybody happy with that? And our value for k is 2. Everybody good with identifying those? Again, not very hard. All we did was use a definition. There's no math, really tricky calculation or anything involved here. What I'm going to do now is I'm going to write down the numbers 1, 2, 3, and 4. Those numbers 1, 2, 3, and 4 correspond to the 4 criterion we listed above. And basically what we're going to do is we're going to check to see if any of these 4 criterion apply to this situation. So if I go back and look at the first criteria, I need to check to see if A is less than 0. What was the A in our situation? Negative 3. So certainly that applies, right? So since A is less than 0, I have a reflection across the x-axis. So I'll write that next to number 1. Everybody happy with that? Okay, now let's look at number 2. Number 2 says if the absolute value of A is not equal to 1. Our A is negative 3. What's the absolute value of negative 3? Positive 3, which is definitely not 1, right? So this applies. And since the absolute value of negative 3 is 3, that's greater than 1, so we have a vertical stretch. So next to number 2, I'm going to write vertical stretch. Okay there. Now we'll go to number 3. When I read number 3, it says if h is not equal to 0, what's our value for h? 0. So that doesn't apply, right? So I'm just going to put a dash there to let myself know that I checked this, but nothing happens. And then lastly, I'm going to look at 4. It says if k is not equal to 0, what was our k? 2. So this one applies, and since 2 is greater than 0, I know we're going to go up 2 units in this case. Everybody okay with how I've used that information? Let's do one more example, and then we'll move on to the next idea here, or the next way we can use this information. So let's say we have y equals 1/2 of f of x plus 3. So we'll start by identifying our values for a, h, and k. In this case, what is our value for a? 1/2. Everybody agree with that? What is our value for h? It's not 3. It's not 0. So if we go back and look, our general form says x minus h, but in our problem we have an addition symbol here. So how can I rewrite plus 3 as a subtraction problem? Minus a negative. So really what I have here is x minus a negative 3. Everybody can see that? So what is my value for h actually? Negative 3. So in general, the rule for the h's is the sign on my h is the opposite of whatever it looks like in my function. So notice I had a plus sign here, but I have a minus 3 as my actual value for h. This is the most common mistake students make when doing these sorts of problems. It becomes a very big problem if you don't catch that and get that straightened out early on. This is why I wanted to do this example in particular, and why I'm spending a lot of time talking about it right now and really it seems like over-explaining this. But it's easy to forget this, and if you forget this on a regular basis, it creates lots of problems going forward. So please make sure we remember the sign on my h is really kind of the opposite of what it looks like in my equation. Okay with that? Good. And what's my value for k? 0. Very good. So next I'll write my numbers 1, 2, 3, and 4. And we'll start checking those 4 criteria. So if I turn back, the first criteria asks, is a less than 0? Is that true in our case? No. So we don't have to do anything there. We'll put a dash because our a is definitely not less than 0. The next thing asks, is the absolute value of a equal to 1? In our case, no, it's not. So something happens. What is the absolute value of 1/2? 1/2. And since that is less than 1, we know that we have a vertical shrink. For 3, it asks, does h equal 0? Our answer is no, so something happens. Since h is less than 0, it's going to go left because it's negative, and then 3 units because the h is negative 3. And then 4 asks, is k equal to 0? Our k is 0, so nothing happens there. Is everybody okay with this idea? So again, not very difficult from a computation standpoint. We haven't actually crunched any numbers here. We're just kind of looking at the behavior of this function, describing kind of what we'd expect the transformed version of the parent to look like. So this one would be shrunk down a little and moved left. Everybody okay with that idea? Now, if we knew what the parent function looked like, we could generate a decent graph, and that's really what we're going to do on our next example. Actually, I want to do this a little bit different spot here. So let's say we're given that this is our parent function, our f of x. And we're asked to graph y equals y equals 2 times f of x plus 1 minus 1. Actually, let's just do that. Put a negative sign there. Okay. I'm going to start the same way I did before. Write down my values for a, h, and k. And then describe my transformation. And then I'm going to use that description to graph my new resulting function. Everybody okay with that plan? So what is my value for a here? -1, right? What is the a doing? What operation is the a doing to f of x? Multiplying. When nothing is there in a multiplication problem, what number do you have to assume it is? 1. If there's no number there in an addition or subtraction problem, what number is it? 0. Okay, so if you don't see an a, it's a 1. If you don't see an h or a k, it's 0. Everybody's okay with that? Okay, what is our h in this case? -1. Very good. And our k? Also -1. All right, so if I look at my criteria for the first one, I have to check to see if a is negative. Our a is negative, so we're going to have a reflection across the x-axis. The second step wants to check if the absolute value of a is equal to 1. The absolute value of -1 is +1, so nothing happens there. In step 3, we're looking at whether h is equal to 0 or not. Our h is not equal to 0. And because it's negative, it's going to go left. And because the h is -1, it's going to be 1 unit to the left. Similarly, 4 looks at the k. Since our k is non-zero, it's going to do something. Since the k is negative, it's going to go down. And since it's -1, it'll be down 1 unit. Everybody okay with that idea? All right. So now what I'm going to do is I'm going to redraw my graph in 4 steps. I'm going to do each one of these transformations one at a time. And the resulting final step will be the actual graph for y equals negative f of x plus 1 minus 1. So the first graph I'm going to draw in blue. And then I'm going to take my blue graph and do the transformation 3 to it and graph that in purple. And then I'm going to look at the purple graph, do the transformation 4 to it, and draw that graph in green. And that'll be my final answer. Is everybody okay with that plan? Okay? So, if I look at number 1, it says reflect across the x-axis. How is the coordinates changing if I reflect across the x-axis? Which coordinate changes, x or y? If I'm reflecting across the x-axis, it'll be the y-coordinate. Very good. And how does the y-coordinate change? It gets negated, right? So it becomes the opposite sign of what it was. So 3, 0, the y-coordinate is 0, so you can't really negate 0. That just stays where it is. For this point, 0, 2 becomes 0, -2. And 4, negative 1 becomes 4, positive 1. Everybody okay with that idea? Okay. So next thing I need to do is go left 1 unit. What's going to happen to the coordinates if I want to shift them left 1 unit? Which coordinate is affected, x or y? X, because we're going left or right. Since we're going left 1 unit, what should I be doing to the x coordinate? Subtracting 1. Everybody agree with that? So, oops, that's negative 3, obviously over there. I oopsie-daisied that. So this becomes negative 4, 0. This would become negative 1, negative 2. And this one would become 3, 1. Everybody okay with that? Okay. The last thing I need to do is shift down 1 unit. Which coordinate is going to be affected by shifting down? The y. And what do I have to do to the y coordinate to shift it down? Subtract, and in this case it's going to be subtracting 1. So negative 4, 0 becomes negative 4, negative 1. Negative 1, negative 2 becomes negative 1, negative 3. And there we go. And 3, 1 becomes 3, 0. So we have that as our final answer. Now this was kind of a mess, right? We had to draw potentially 4 graphs to do a problem like this. It kind of ends up all over the place. Is there an easier way to do this? Is there a way for me to just go from f of x all the way down to the green graph in one step without having to mess around through these intermediate ones? There is. So what I can do is I can take my original points from f of x, and I can do the following to each of the x's and y's based on the values for my a, h, and k. And what will spit out are the points in my green graph. So for example, if I start with my points from f of x that were given to me in red, the x coordinate is negative 3, my h is negative 1, my a was negative 1, the y coordinate is 0, and the k is negative 1. So when I do that, I get negative 4, negative 1, which if I look, is the resulting endpoint from our green graph. If I do the same thing here, my x coordinate is 0, my h is negative 1, my a is negative 1, my y coordinate is 2, and my k is negative 1. So that's going to give me negative 1, negative 3, which if I go back and look at my graph in green, is the bottom point from my green graph. So my last one, my x coordinate is 4, my h is negative 1, my a is negative 1, my y coordinate is negative 1, my k is negative 1. When I do that computation, I get 3 and 0. And again, what do I notice there? My rightmost point on my green graph is 3, 0. So whether you want to do this graphing by doing, like drawing the intermediate transformations, or do it all in one shot using this formula. Either way is fine. Okay? So this concluded the material from Chapter 1.